Hey everyone, welcome. Today we're tackling Leetcode problem 2999, count the number of powerful integers. It sounds a bit fancy, but don't worry, we'll break it down step by step. Ready? Let's dive in. Alright, so here's the official problem description. Take a moment to skim it. Got the gist? Essentially, we're given a range, defined by a start and finish number. We're also given a limit for digits, and a special suffix string. So what's our main goal? We need to count certain numbers within a given range. These numbers are called what makes a number powerful. Two things. First, it has to end exactly with the digits given in the string. Second, every digit used to make the number must be small, specifically, less than or equal to the given. We need to find how many numbers fit both rules and fall between and. Let's look at an example. Start is 1, finish is 6000, the limit for digits is 4, and the required suffix is OK. Which numbers work? Well, 124 itself works, it ends in, and its digits, 1, 2, 4, are all less than or equal to 4. How about 1124? Yes, ends in digits, are less than equals 4, same for 2124, 3, 124, and 4, 124. What about 5124? It ends in but oops, the digit is bigger than our limit of 4, so 5124 is out. In total, we found 5 powerful numbers in the range. Okay, so the first idea that might pop into your head is, well, let's just check every single number, from all the way up to, for each number, we see if it ends with, and then check if all its digits respect the limit. Seems simple, right? But look at the constraints. The number can be massive, like 15 digits long. Checking billions or trillions of numbers one by one? That's going to take forever. We definitely need a more clever approach. Whenever you see a problem asking to count things within a large range, a common trick comes to mind. Instead of counting directly in the range, we can figure out how to count everything up to b, and then subtract the count of everything up to a-1. Make sense? So if we can solve the problem count powerful numbers less than or equal to n, we can use it twice to get our answer for the range. So our new core task is building a function, let's call it calculate n, that counts how many powerful integers are less than or equal to n. Remember those two rules. Ends with and digits are no bigger than this type of problem. Counting numbers up to n based on digit properties is a classic candidate for a technique called digit dynamic programming, or digit DP for short. How does digit DP work here? Imagine we're constructing a number digit by digit, starting from the leftmost position. As we build it, we need to make sure we don't accidentally create a number larger than n, and also that we respect our powerful integer rules. To do this, we use a recursive function, and we need to keep track of a few key pieces of information, our DP state. We need to know the current digit position we're deciding whether we're bound by the digits of n, and whether we're currently placing leading zeros. Now, how do our specific rules fit in? First, the digit limit. When we choose a digit for the current position, it obviously has to be less than or equal to our coordinates. And, if we're in a situation, meaning the number we've built so far matches the prefix of n, our chosen digit also can't be bigger than the digit n has at this position. Second, the suffix. This is the trickier part. Once we've placed enough digits that we're definitely forming a number, not just leading zeros, and we're in the last few positions that correspond to where the suffix should be. The digit we choose must match the digit expected from at that position. If it doesn't match, that path is invalid. Okay, let's look at the code structure. Here's the main function count powerful integers. First, we convert finish to a string. We also need start, 1. So we have a little helper function, subtract_1 to handle that correctly, even for cases like 1000 becoming 999. Then, a quick sanity check. If any digit in the required suffix is already bigger than our no powerful number can exist, so we return 0 right away. Finally, we call our main counting function, calculate for finish and start, 1, and subtract the results. We also set up some class variables to hold s, limit, etc. for easy access in the helper functions. Oh, and we might need to increase Python's recursion depth limit for very large numbers. Now inside the calculate function, which counts powerful integers up to the number represented by num_str. First, some edge cases. If num_str is empty, like when start was 1, the count is 0. Also, if the number n itself has fewer digits than the suffix s, It's impossible for any number ending in s to be less than or equal to n, so we return 0. We do another quick check on the digits in s against the limit just to be safe. Then, we store num_str as the target we're aiming for, clear any old results from our memoization table, and kick off the main recursive digit dp function, which we call dfs. We start at index 0, with the constraint active, since we must stay less than equals n, and we are initially in the "leading 0 state. Alright, let's dive into the dfs function. This is the heart of the digit dp. First, the base case. If our index idx reaches the length of our target number string, it means we've successfully placed all digits. We return 1, signifying we found one valid number, unless we were in the state the whole time, meaning we just formed the number 0, which isn't positive or powerful, so we return 0 in that specific case. Next, we check our memoization table, self.memo, to see if we've already computed the result for this exact state. Index, tight, is _leading. If yes, we just return the stored value. If not, we calculate the upper limit for the digit we can place. It's either the digit from our target number, if is true, or simply 9, if we're no longer restricted. We also consider our overall. Then, we loop through all possible digits, from 0 up to the minimum of our allowed upper bound and the global limit. Inside the loop for each possible, we perform our checks. The important one is the suffix check. We only need to worry about this if we're actually placing a meaningful digit, meaning we are past any leading zeros, or the digit itself isn't 0. And if the current position idx falls within the last s_len positions of the number, relative to the end. If both conditions are true, we figure out the corresponding index within the suffix string s, and check if our current digit matches the required suffix digit. If it doesn't match, we continue to the next possible digit. This path is invalid. If the digit passes all checks, implicit limit check by loop bound, explicit suffix check, we determine the state for the next recursive call, will it still be leading 0, and add the result of that recursive call to our running total res. Finally, after trying all valid digits for this position, we store the computed result res in our memoization table for the current state and return it. So how efficient is this digit dp approach? Much better than checking every number. The time complexity is roughly proportional to the number of digits in the number. Why? Because our dp state depends on the digit index, idx, which goes up to the number of digits. The AND flags just add small constant factors, 2 options each. Inside each state, we do a small loop, at most 10 times. So we often say this is big O of log n time, or order log n time, where n is the value of. The space needed is also proportional to the number of digits, mainly for storing the dp results in the memoization table, and for the depth of the recursive calls on the system stack. Alright, let's quickly recap. We needed to count powerful integers in a range, numbers ending in with digits under a limit. The key was realizing direct range counting is hard for large ranges, but we can use the standard trick, count up, to then subtract the count up, to start -1. The core counting part was solved using digit dp, building numbers digit by digit, while keeping track of whether we're restricted by n, and handling leading zeros. We carefully integrated the digit limit and the crucial suffix matching constraint into the dp transitions. Hope that breakdown made sense and helped clarify the approach. If you found this useful, hitting the like button would be awesome. Feel free to subscribe for more Leetcode explanations, or leave a comment if you have any questions or maybe a different way to solve it. And hey, if you're feeling extra supportive, the Boba Fund is always appreciated. Keep practicing, keep coding, and I'll see you next time.